So now we are talking about dependent events. So this is when the outcome, guys, thank you so much. The second thing to happen has been affected by the first. So let's read the example that they've given us here. 7 red marbles, 3 marbles in the bag again. I'm going to choose a marble randomly, but then I'm going to keep it out of the bag, and then I'm going to choose a second marble. So when I go to choose that second marble, it's a different scenario than it was the first time.
Yes, you have to change the numbers.
Correct. So how do I find the probability of that? I'm still going to find the probability of each one and multiply them together, but the second one has changed now. So let's take a look at this one. Probability of choosing a red and then choosing a red again. So when I choose the first red marble, what is the probability of choosing that first red marble? 7 out of 10. But now, the second time, it's only 6 out of 9. Think about it. There is one less red marble in the bag because you took it out. So now there's only 6 red marbles, and there's not 10 marbles total in the bag anymore. There's only 9. So you have to think about it. So in this case, I'm here, and now again, I'm going to multiply. You can reduce first if you want. Doesn't matter. I am just going to multiply these together. So I might just reduce 6/9 to be 2/3. Make mine, and then I can reduce the 2 and the 10. However you do it, you should end up with 7 over 15. Whether you reduce at the end or before you multiply, I don't care. It's a little bit easier if you do it before you multiply. Keep your number smaller. But did everybody get 7/15? And you can see that that's quite different than the same event when we were replacing the marble. That was just 7 out of 10 times 7 out of 10. It was 49 out of 100. Okay, so it changes things quite a bit, whether you are going to replace the item or keep it out. All right, now we're going to do the same thing, but for blue marbles. So it's a probability I pick a blue marble the first time. 3 out of 10. Now I'm going to keep that blue marble out, and I'm going to reach back in. 2 out of 9. So I'm going to reduce first. Yes, I can. I just did. When you are multiplying fractions, remember that anything in any numerator can reduce with anything in any denominator. They don't have to be in the same fractions. So, did you get what I got? Oh, good. Now, this is different. Please make sure that you're paying attention here. Let's choose a blue marble now the first time. Probability is? Right. I picked out a blue marble. Now I want to reach in and pick a red marble. There's still 7 red marbles in there. I haven't picked one out yet. I picked out a blue marble. So when I reach in, I still have 7 red marbles. But how many total marbles are there? 9. Do you see that? That's an important difference. So it depends. Like in the last 2 that we did, you were trying to pick the same color marble again. So I had to take one away from the numerator and the denominator. But here, that's different. Okay, so I'm going to reduce. So I get 7 out of 30. Okay, you guys choose, try 4 without me telling you what to do. Okay. Sure. Destiny, what's the probability I will choose a red marble?
I said 21 over 90.
Just for the first one, for the first red marble.
Oh, 7 over 10.
7 out of 10, I agree. Now I want to choose a blue marble. How many blue marbles are there when I go to pick that second marble?
3 over 9.
Yes, perfect. Do you all agree? Good. So we can reduce. All right. Now, let's try a red marble 3 times in a row. Go ahead and try 5 before we talk about it together. Everybody's got an answer? All right, choosing the red marble the first time. 7 out of 10, that's easy. Now I want to pick another red marble. 6 out of 9. And now I want to pick another red marble. Yes. Does that make sense to everybody why this happened?
Wait, how'd you get the 6? Because
I took 1 red marble out, so now there's only 6 red marbles left when I go to pick it the second time. And then when I go to pick it again, now there's only 5 red marbles left in there. So, yeah, I'm going to reduce some things. Seven over 24.
how do you get 7 over 24?
By reducing.
Well, if you say you just multiplied like straight across without like simplifying, would you get 210 over 720?
Probably, but now you got to reduce that.
Okay.
And then it should reduce right back down to 7 over 24, but that's so much more work. Okay, everybody try 3 blue marbles in a row. Don't tell anybody your answer. Supposed to be doing 6.
Oh, I didn't. Oh, I thought you said you have to have it.
Okay, everybody should have an answer by now. Who wants to give it? Go ahead, Gianna.
1 out of 120.
Yep.
I was like, missing.
You're such a good actress.
You should be in the play.
I should get an Oscar.
I should get a Toscar. You should get a Toscar. That's a fantastic Toscars.
I'll vote for you next year. To save you. The greatest math.
Oh.
Even though it's not
It's like the Dundies. I don't know if I want one.
Yeah, oh my God. We should watch the Office.
Okay. So,
We couldn't have that kind of award show because people were like, everyone needs to be included.
flip it over, everybody.
There's a back. Haley.
So, before we start, I always find that not everybody knows how decks of cards are split up.
Nailed it.
52.
Yes. In a deck of cards, in all, you have 52 cards. There are 4 groups called suits. There are 13 of each of them. There are 13 hearts, 13 diamonds, 13 spades.
Artist. You should get
I know, that's perfect. And 13 clubs.
My brother broke my
As you might imagine, the hearts are red, as are the diamonds. Spades are black, as are clubs. Okay, and then in each, ow, oh, I just bit my tongue. Oh. I have those.
Hey, why is that so funny?
Anywho, you've got in each of these suits, you have the following cards. You have ace, king, queen, jack. And then you have the number cards. 10, 9, 8, 7, 6, 5, 4, 3, 2.
Wait, there's a one?
No,
I thought there was only 4 of each.
there are.
My grandmother really had a lesson on house. Like, so this
Do you remember when we used to play it in sixth grade?
All right, guys. So, let me ask you some questions here. Let's say we are playing a game with a standard deck of cards, which is laid out as I have described here. Can you please stop talking? Thank you so much. What is the probability that you select a 7?
Like,
4 out of 52. Or
give me 1 second.
there's 4 sevens altogether. There's a heart, a diamond, a spade, and a club.
Oh, there's 2 Wait, was it 113?
1 out of 13, yes. All right, guys, please. What is the probability that you select a heart?
13 out of 52.
Which is 1/4, right? And doesn't that make sense? The hearts make up 1/4 of the whole deck. So you have a 1 out of 4 chance of selecting a heart. What is the probability of you selecting any red card?
1/2.
1/2. That's half the deck. What's the probability of you selecting a 7 of spades?
1 out of 52.
There's only one 7 of spades, so it's 1 out of 52. What is the probability of you selecting a face card? The face cards are king, queens, and jacks. So any king, queen, or jack. It does not include the aces. 12 out of 52, which is
6, 6. What am I doing? 3, 1.
3 out of 13.
That's what I meant.
What is the probability of you selecting any card that is not a 2?
48 out of 52.
12 out of 13. Okay, let's make things more interesting. Let's say we're going to select 2 cards now.
Getting intense.
What's the probability you will select a 2 and then select a 2 again? Oh, you guys are being too quick. The right answer is, I can't answer that yet, because you didn't tell me if you put that card back or not. Because it's 2 totally different answers, right? Yeah. Let's assume that you put the card back. So I want you to pick a 2, put it back, and then I want you to pick a 2 again. Any 2. It doesn't have to be the same 2. Any 2. I only have the reduced answer, so maybe. I agree with Kristen. The first time, it's a 1 out of 13 chance that you will select a 2. I know it's 4 out of 52, but isn't that 1 out of 13? So then it's a 1 out of 13 the second time, 1 out of 169. All right. Now I want you to pick the same 2. So let's pretend you pick the 2 of diamonds. You put it back in, and I want you to pick the 2 of diamonds again. So now it's a specific 2. It has to be the 2 of diamonds. You're going to pick it, put it back in the deck, and then you're going to pick it again. 2 of diamonds. Yep. Pick 2 of diamonds, put it back in, pick 2 of diamonds again. I can't do that in my head.
Oh, the number 2 diamond.
Right. 2 of diamonds. Nope. Yes. Think about it. What's the probability that I pick a 2 of diamonds the first time? 1 out of 52. So when I put it back in, the second time is 1 out of 52 again? So I just got to do 1 out of 52 times 1 out of 52, which is 1 out of 2,704. This might actually be a good time to talk about the difference between experimental and theoretical probability. So, what we just did, right? We got 1 out of 2,704. That means if I literally tried this, I would expect that if I did it 2,704 times, where I picked a card, looked at it, put it back in, and then pick that same 2 of diamonds again. If that was really my goal, it would take me on average 2,704 times before that happened. So every 2,704 times that I do it, I'm probably going to have that happen 1 time. You follow me? Say I really did that. Say I sat there and I did it 2,704 times. Am I guaranteed to have this happen? No, it may never happen. I could sit there all day until I'm blue in the face. So there's a difference. Right. So experimental probability is what actually happened. So I could do it 2,704 times. And maybe I picked the 2 of diamonds and then I picked it again. Maybe that happened 10 times in that 2,704. Who knows? It's possible, right? It could keep happening. So, experimental probability is what I actually did the the experiment and I tallied up how many times it actually happened. Theoretical probability is what we are calculating. Okay, so in theory, if I flip a coin, right, I have a 1 out of 2 chance of landing on tails. Could I flip it 10 times and never get tails? Sure, it could happen.
Oh, we did this in bio.
Oh.
Yeah.
So, experimental and theoretical probability don't always match. Usually, they, you know, that's if you ever go to, gosh, when you get old enough to go to the casino, there's one thing like if you ever see a roulette table, they usually tell you like what the last, I don't know, 20 or 30 spins have been. And there'll be a graph and it'll show you how many times has this ball landed on the 4, for example. How many times has this ball landed on the 13? And it shows you what actually has happened over the last 50 spins or 20 spins or whatever it is. Oh, they're not lying. But how am I supposed to pick the next one? So sometimes I'm sitting there and I'm like, okay, so it's landed on 4 a whole bunch. So in my head, you got to go one of either 2 ways. Is it going to keep landing on 4? Or, okay, 4 is done. Now it's going to, it's landing on 4 so much. Now it's got to land on the other numbers. You never know. Because one spin has nothing to do with the next spin. For the next 6 hours, it could just land on 4. You don't know. You have no idea. So, anyway. Next time I'm there, I'll try and sneak a photo so I can show you.
You're not allowed to take pictures?
No, you're not supposed to.
That's so stupid.
I don't know.
That's like a concert. They're like, no photography.
Well, I tell you what, when MGM in Springfield just opened, my husband and I got to go to like a preview night before it was open to the public. It was so cool. So it was like the first time anybody was there, like being able to play. I didn't know, so I had a Facebook Live going. Because everyone wanted to see what it looked like on the inside. I'm like, oh, look, this is so cool. And then I heard someone else getting yelled at, and I was like, oh. So.
I'm gonna end this live, guys.
That was funny. All right.
Go subscribe to me at Erica's Found videos.
All right, guys. So what I would like you to try now, if you look at the back sheet of the one that we were working on.
Yeah, I don't get the way it's worded, so it's stupid.
I actually want to change the directions a little bit. On the top here, it says, on this side, anytime you are choosing more than one card, you will not be replacing the cards already drawn. I want you to add a line. So, let's see. Drawing 3 cards that are all queens from a deck of cards. Oh, yeah, no, I want it like it is. Yeah, okay. So, are these independent or dependent events if I'm not putting the card back? Dependent, because the second one has now been affected. It depends on the first. It's changed now. So we are not putting the cards back on this side. All right? So try these 15 problems. We should have enough time to go over the answers before the end of class, and then I can give you your homework.